Okay, hi boys, I just want to give you a quick video on the end of the last property of logs that we didn't quite cover in class. So the last one that we didn't quite talk about was the change base formula. And the change base formula tells us that I can go ahead and write any log that has some base. So example, in this case, log base b of x. I can go ahead and basically change the base of this log to be some other value. So in this case, to do it, you go ahead and take log of whatever your new base is of x, so whatever your argument is, and divide it by log base a, again, that new base of whatever the original base was. So that basically tells us we can go ahead and change it to a base that we like instead of one that we don't like. We are going to go ahead and take a look at the proof of this. It should be fairly straightforward. And then we'll get into the very last bit of this lesson. So in order to prove this, we're going to go ahead and we're going to start with the assumption that log base b of x equals some value y. It's not right. Okay, so we're starting with log base b of x equals y. This implies if we go ahead and change this to an exponential, this means that we have b to the y will equal some value x. So in order to work with this equation, we do want a log base a of x to show up. So again, remember, we're proving that log base b of x is actually the same as log base b of log base a. We're changing the base in this case. A of x divided by log base a of b. So in this case, I'm kind of starting with this expression here that I have. And I'm going to go ahead, we want to kind of force some logs back into this expression. So I'm going to go ahead and instead of converting this log base b of y equals x to a log, I'm going to go ahead and take the log of both sides. And we're going to do this with respect to the base a because that's the base that I want to show up eventually. This does look a little bit different than what you're used to, like taking the log of both sides. But it turns out that this will kind of help us when we're going to solve equations. And it turns out that as long as I perform the same operation to both sides, I can kind of do whatever I want. Now, as we see, the expression on the left-hand side is one of our properties of logs that hopefully we remember from last class. But the idea is that we can take this exponent y that I have going on, and I can go ahead and drop that down in front. So we're going to go ahead and rewrite this a little bit, change it to y times log base a of b equals log base a of x. And one of my initial assumptions was that y equaled log base b of x. So I'm going to go ahead and substitute this in for y. So I have log base b of x times log base a of b equals log base a of x. And in this case, we want to go ahead and get our log base b of x by itself. And to do that, we can go ahead and divide both sides by this log base a of b. And it turns out we'll basically get our initial, or what we want to show. So we can divide both sides by log base a of b, log base a of b. The two on the left-hand side will cancel out, and I am simply left with log base b of x equal to log base a of x over log base a of b. And that is my proof. The change of base formula was really, really helpful when calculators didn't have the ability to find logs of various bases. However, a lot of ours are able to do that now. Obviously, the world's gotten better. Technology has gotten better, so we're able to do that. So in order to do this, we are going to go ahead and try this using a calculator just so you see what this looks like. So in this case, we're going to try and find log base 2 of 9. So if you're working on a regular TI-84 calculator, drop this down. To find our log function, we're going to go ahead into math. And all the way at the bottom, I believe it's option A, is log base. So if we choose this option, it allows us to, there it is, we can type in whatever base we want. and whatever argument we want, and very easily find the decimal. So in this case, 2 raised to the 3.1699 power would give us 9. The 3 point, let's actually just bring that screen up. 3.1699, 1699. I guess this goes up here. We can go ahead and check to see if different bases would work as well. In this case, we're going to go ahead and try log base 10. If you're using log base 10, you can go ahead and just hit the log button that's on your main screen. So I have log of 9, and we're going to divide this by log of 2. And if this change base formula is correct, I should again get that 3.1699. And it turns out that I do. So we still get 3.1699. Even a different base, if we wanted to try ln, again, we should get the same option, or we should get the same answer. So trying this, change that to 2. There we go. And I get the same number yet again. So in this case, it doesn't matter what base you use. You will get the same answer every single time using this change of base formula. If you have one of the slightly older calculators and yours does not have that log base option when you go to math, you will have to use a change of base formula in order to plug this into your calculator. You will see a couple problems throughout the rest of the chapter where we will be plugging values like this into our calculator. However, they won't become as important, so it's okay later if we don't have that. The last thing that I wanted to talk about here was if we consider these two functions, f of x equals ln of x squared and g of x equals ln of x. By the power rule, so that one exponent rule, these should be equivalent expressions. However, it turns out they're not quite the same because if we remember about logs, we cannot take the log of a negative number or of 0. And in this case, this ln of x squared, this would force x squared to be bigger than 0, which means that x has to be, it appears that x would have to be greater than 0. However, because it is squared, I could plug in a negative value into this log. So if I plugged in, if I tried f of -1, this would be ln of the quantity -1 squared, which we know is just ln of 1, which is actually just 0. So it turns out that our domain would actually kind of show up like those radicals did before, where we have that x needs to be strictly bigger than 0, or x could be strictly less than 0. Again, that's kind of coming from taking the square root of 0 and that plus or minus sign showing up. However, obviously this is different than g of x, because in g of x, I just have the input of x, and that tells me that strictly x has to be bigger than 0. There's no option to plug in a negative. If I plug in a negative, you're going to get a non-real answer. It is undefined. So these aren't quite the same function, just considering what the domain is. If you want to see the graph of these things, go ahead and graph them. You'll see they are slightly different. And just as an example, we have seen this kind of thing before with our rational functions. So in this case, in f of x, you could go ahead and factor the top. We would see that our x plus, we'd have a set of x plus 2's we could cancel out, which seems to yield the same function as g of x. However, the function for f of x would have a whole at -2. So all that being said, this does round out all of our properties of logs. So you have the 3 that we covered during class, and then this change of base formula. With this being said, you should be able to try out that homework. And if you have any questions, let me know.